Welcome to Unit 7. Unit 7 is going to talk about differential equations, which is an extremely important application of calculus. In fact, it's so important that at most colleges and universities, it has its own class to focus on it. Okay, a differential equation in x and y is an equation that involves x, y, and the derivatives of y. Now, of course, it doesn't have to be x and y. It could be any variables, but in here, we're just talking about x and y for that particular sentence. A solution to a differential equation is a function that satisfies the differential equation when the function and its derivatives are substituted into the equation. A solution can either be one function, which is called a singular solution, or in fact, usually the AP test would call it a particular solution. So instead of singular, it would be particular. Or a set of functions, which is called a general solution. Okay, so here's some examples of differential equations. The first one says, actually all three of them say the same thing, just with different notation. The second derivative of y plus 2 times the first derivative of y would equal 3 times the original function of y. Okay, and the other two are just the same way, just written a little differently using different notation. So in this first part here, we're going to talk about variation, direct versus inverse variation. Direct variation occurs when a situation gives rise to a linear function, where k is the variation constant or constant of proportionality. What we say is that y varies directly as x, or that y is directly proportional to x. Inverse variation occurs when a situation gives rise to a function like this, where k is the constant of proportionality again, but we say y varies inversely as x, or y is inversely proportional to x. So to sum this up, if you see directly, you're going to do k times x. If you see inversely, you're going to do k over x. So number one, a particle moves along a straight line. Its velocity, v, is inversely proportional to the square of the distance, s, it has traveled. Which equation describes this relationship? All right, so take this English sentence and convert it into a mathematical sentence. So the velocity, so v, is, so equals, inversely proportional to, so that means k over something, the square of the distance s, so s squared. Okay, so which function looks like that? Question B. I'm sorry, answer B. V of t equals k over s squared. Number two, a puppy gains weight, W, at a rate approximately inversely proportional to its age, T, and months. Write an equation that describes this relationship. So, puppy gains weight, W, but we're not talking about the actual weight. We're talking about the rate of W. So the rate of W would be W prime, or dW dt. W prime or dW dt would be fine. Inversely proportional, so k over its age, t. So dW dt equals k over t. So the big difference between this one and the last one, this one we're actually talking about the velocity, not the rate of the velocity. This one we're talking about the rate of the weight gain. That's why it's dW dt. The learning rate for a skill S is proportional to the difference between the maximal potential for learning that skill M and the amount of that skill already learned, L. Write an equation that best describes this relationship. Okay, so first of all, the learning rate for a skill, so we know this is going to be ds dt, because it's a rate, is proportional. So it doesn't say inversely, it doesn't say direct either, but if it doesn't say inversely, we can assume it's direct. So it's going to be k times the difference between, so we know that's subtraction, the maximum potential M and the amount learned L. So maximum minus the amount learned already. So that's our equation that we would have for this differential equation. Number four, an IV drip administers medication to a patient's bloodstream at a rate of 3 cubic centimeters per hour. The patient's organs remove the medication from the patient's bloodstream at a rate of proportional to the current volume V of medication in the bloodstream. Which equation best describes this relationship? Okay, so we want to know it's telling us here, let's highlight this, the rate of proportional to the current volume V, I don't need to go that far, proportional to the current volume V, okay? So we want to know the volume, and it's proportional to its own volume. So depending on how much is in there, that's how quickly the rate will be decreasing, okay? So the rate of volume, we're going to say dV dt for that one, okay? And then we're going 3 cubic centimeters per hour are going in, and then we're going to subtract because we're removing our rate proportional. Again, it doesn't say directly or inversely, so we can assume it's directly. So K times the current volume V. So the new volume is going to be adding 3, but also subtracting K times V per hour. So that would be, let's see here, it looks like A would be our matching answer. And number 5, a chemical is diluted out of a tank by pumping pure water into the tank and pumping the existing solution out of it. So the volume at any time t is 20 plus 2t. The amount Z of the chemical in the tank decreases at a rate proportional to Z and inversely proportional to the volume of solution in the tank. Which equation describes this relationship? All right, so again, we're talking about how much is in there, the volume of it, the rate at which it's increasing or decreasing. The amount is called Z, so we're going to call this dZ dt. So this is a tougher one here. It says it decreases at a rate proportional to Z, so that means directly proportional, and inversely proportional to the volume of solution in the tank. So let's start with the first half. It decreases at a rate proportional to, so negative Kz decreases at a rate proportional to that. But then inversely, so divided by the rate at the current time, how much is in there at the current time, which is 20 plus 2t. So that would be what our proportion, our direct variation and inverse variation combination would look like. We're multiplying the direct variation and dividing the inverse variation. And this is what our differential equation would look like. And that looks like it would be answer A. All right, that's an introduction to differential equations. As we move on in this chapter, we'll start graphing these differential equations, which is actually called graphing a slope field, and then solving them later on for the general solutions or the particular solutions. But that's it for today's video, everyone. Thank you very much for tuning in, and we'll see you again soon.